Now we will see some other results. If you see the problem here, our problem was laminar flow over a heated cylinder. The parameters were like this. Our working fluid is air, our cylinder diameter is 2 inch, a cylinder wall temperature is 80 degrees centigrade, inlet velocity based on Reynolds number 100, that is laminar flow, and our inlet air condition was 25 degrees C. And we have to find out the contour for velocity, temperature and pressure. That we have already done. We have to plot some velocity, temperature and pressure at D, 2D and 3D downstream location. We already have done that also. Now we have to find out the surface heat transfer coefficient, average Nusselt number and total heat transfer. We can find these three parameters. If you go here in the fluent, in the results section, you have the last option, report. So if you go here and if you see this report option, you have lots of different options like flux, force, projected area, surface integral, volume integral and other stuffs. So if you go to flux and go to setup, then you can see here in the option you have the mass flow rate, total heat transfer rate, radiation heat transfer rate. You can find all of these fluxes. So in our case, we want to find out the total heat transfer rate. So click the total heat transfer rate, and the boundary is cylinder wall because heat is transferring from cylinder wall to the environment. So select this and select compute. Here you will see in the display window, in the text window actually, here you have the total heat transfer rate, cylinder wall, that is 5.59 watt. So this is the total heat transfer rate. This much heat is transferred from the cylinder to the outside environment. And you can save this if you go to right option and you save it as a heat transfer. Select OK, then it will save it as a text file. If you go here and if you double click, you can open it in Notepad. You can see the flux report. Now we have other two parameters, surface heat transfer coefficient and average Nusselt number. We can also find these two parameters. If you go here in the report section, go to surface integral, setup, then report type, select area weighted average, field variable, select wall flux, and in the field variable wall flux section, select surface heat transfer coefficient. In the surface, you have the cylinder wall surface, select the cylinder wall and compute. So here you have the surface heat transfer coefficient, that is 2.13 watt per meter square Kelvin. So this is the H value, and if you go here, we want to check our H value with analytical calculation. So if you go here, this is the Nusselt number calculation, the analytical calculation for flow over a cylinder. This is a famous correlation published by Churchill and Bernstein. In this correlation, the variables are the Reynolds number and the Prandtl number. In our case, the Reynolds number is 100 and Prandtl number is 0.7 based on the average film temperature. So if you put these two values here, you will get the Nusselt number 5.15. And from the definition of Nusselt number, we know that Nusselt number equals to HD over K. This H is the heat transfer coefficient, D is the characteristics length, Here is the characteristic length is our diameter of the cylinder, and K is the thermal conductivity of working fluid. So here our K is 0.024, our diameter is 0.05 meters, that is 2 inch. So if you put this value in this Nusselt number equation, then you will get the H value is 2.453. So this H is our analytical H, and this 2.135 is our got this H from our simulation. So you can see the comparison with the analytical calculation here. With this, you can find lots of other parameters. In the next tutorial, we will see the same problem, but the flow condition is turbulent. So we will see flow over a cylinder at a turbulent flow, and we will find the same parameters and everything in turbulent flow condition. Thank you.